All right, welcome back everybody. Here we are, section 10.15, representing functions as power series. Congratulations. This is the final lesson of the course. Woo! We made it. It says right here, in this lesson, we're not going to really be learning anything new. We're just going to put some things together that we've already learned in some different contexts. We're going to look at a bunch of examples about how we can, represent functions and manipulate functions when they are represented as power series. We talked in the last lesson about the fact that we could take a known Maclaurin series or a known Taylor series and we could substitute values into that series, or we could add things to that series or subtract things from that series, or multiply. Last lesson we multiplied by some like monomials once we found a series. But really we can multiply by a polynomial. We could multiply by another series. And we could even though we didn't do it at all in the last lesson, we can even modify these series by, using integration or differentiation. And so there are a whole lot of things that we can do in order to represent functions and manipulate functions when they're written as power series. And in this final lesson of the unit, we're just going to look at a few examples of where we do that, and then you're going to give that a try for yourself on a few examples in some different contexts. All right, so let's look at the first example, example 1. Let f be the function f of 0 equals 2, and derivative f prime of x equals 1 over 1 plus x to the fifth. What is the Maclaurin series for f of x? All right, so first of all, we're trying to find the Maclaurin series for f of x. We know the function f prime. So in order to get the Maclaurin series for f, it would be nice to have the Maclaurin series for f prime. Now this series looks a lot like one of the common Maclaurin series that we needed to know, namely the series 1 over 1 plus x. This looks a lot like that. So 1 over 1 plus x is 1 minus x plus x squared minus x cubed plus negative 1 to the n times x to the n. Well, that's it, times x to the n. I went like I was going to divide it, and then I realized I was like, oh, divided by 1. Uh-oh. This might be one of those times when, oh, come on, don't crash. Folks, I might be back with you. What would the last lesson of the year be without my presentation software crashing? All right, so let's get back into it. Sorry, I at least paused and you didn't have to go through the whole crash with me and the restart. So there's our series for f prime of x, or pardon me, for 1 over 1 plus x. Now f prime of x, which is equal to 1 over 1 plus x to the fifth, I can get from this series by just replacing all of the x's with an x to the fifth. And so this is going to be the Maclaurin series for f prime 1 minus x to the fifth plus x to the 10th minus x to the 15th plus negative 1 to the n x to the 5n dot dot dot. Okay, so this is my series for f prime of x. So now, if I want a series for f, what do I do with f prime? I'm going to integrate it. And so I integrate f prime, that's going to give me f of x, and that's going to be equal to the integral of this whole series. Now, normally when we integrate something, we put, the constant of integration at the end. But since this is an infinite series, I'm going to lead with the constant of integration because, the terms in this series never end. So I'm going to put a constant out front. And then I'm going to just integrate this term by term. The integral of 1 is x. The integral of x to the fifth is x to the 6th over 6. The integral of x to the 10th is x to the 11th over 11, etc., etc., all the way out to my general term, negative 1 to the n times x to the 5n plus 1, all over 5n plus 1. Now, we've taken care of everything except for the constant, and we've got this initial condition that we see here, that f of 0 is equal to 2. When I put 0 into this function, all of these terms except for the constant drop out, and so the constant is just going to be 2. And here is my function, or my series that represents, that's a really bad x to the 6th, my series that represents f of x, given all of the conditions of the problem. All right, there's my series for f of x. Okay. Next example. I'm going to clear off example 1. If you need to look back at it, go ahead and rewind if you need to look back at it. We're going to move on, but it was covering up example 2 for me. Let's go ahead now and look at example 2. In example 2, we're going to find the third degree Taylor polynomial about x equals 0 for g of x equals sine of x over 1 plus x. So a couple of ways that I could do this. I could try and take the sine of x, the series for that, and do long division, divide by 1 plus x, do long division. I don't know if that's what I want to do. Or I can think about this as sine of x times 1 over 1 plus x. Both of those are series that we know. And so if I think about g of x is equal to sine of x over 1 plus x, that's equal to sine of x times 1 over 1 plus x. And then I think about the series for these two. Sine of x is what? It is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc., etc. I'm not going to need any more of the terms for that because we're trying to find a third degree polynomial. So the biggest power of x that we need is the third power. And I'm going to multiply that by the series for 1 over 1 plus x, which is 1 minus x plus x squared minus x cubed, etc., etc. Now, as I multiply this out, remember we're trying to find the third degree Taylor polynomial, so all we want is terms up to the third power. So what I'm going to do is I'm going to take the sine series and multiply that times the terms from the 1 over 1 plus x up until I get to the third powered term. So I've got x times 1 is x, and x times minus x is minus x squared, and x times plus x squared is plus x cubed. Those are all the terms that will appear in the third degree Taylor polynomial from that. Now, I also need to do the same for the second term of my series for sine of x. So I'm going to multiply x to the 3rd over 3 factorial times 1, so that's minus x to the 3rd over 6, and that's the only term that's going to be in the third degree polynomial based off of this term times 1 over 1 plus x. And now all I need to do is combine my like terms in my series, and therefore the polynomial, third degree Taylor polynomial, is going to be x minus x squared plus 5x to the 3rd over 6. All right, kind of cool. Now, we didn't talk about intervals of convergence with these, but here in this one, in example 1, the interval of convergence for f prime was from -1 to 1. The integral of that will have the same interval of convergence. The only difference is we don't know whether the endpoints are included or not in either of them. And so we would have to check the endpoints independently in order to decide if they converge or not. All right. But -1 to 1 is our base interval of convergence for that one. For this one, the interval of convergence for sine of x is all real numbers, the interval of convergence for 1 over 1 plus x is from -1 to 1. That means that this polynomial, if we expanded it out into a series, it would converge from -1 to 1, the lesser of the two intervals of convergence. All right, example 3. Let h of x be the function represented by the series below, sum from 1 to infinity of x to the 2n over n squared. Write the first three terms for the series for h of x. So we're going to substitute, this is h of x, so we're going to substitute 1 in here for n first. So that's x squared over 1 squared. And then I'm going to put 2 in here. That's going to be x to the 4th over 4. And then my third term, I'm going to put 3 in here. That's going to be x to the 6th over 9. Those are the first three terms of the series for h of x. And this, by the way, is the general term, x to the 2n over n squared. All right. Now we want to write the first three terms and the general term of the series for h prime of x. And so since this is h of x, h prime of x is going to just be the derivative of this. And I can just go ahead and take the derivative term by term. Derivative of x squared is 2x. Derivative of x to the 4th over 4 is just going to be x cubed. The derivative of x to the 6th over 9, it's going to be 6x to the 5th over 9, or 2/3 x to the 5th. And my general term, well, it's going to be 2n times x to the 2n minus 1 all over n squared. And now I'd like to simplify this general term. And so this is going to be written as h prime of x equals 2x plus x cubed plus 2/3 x to the 5th plus, and then this is going to be 2 times x to the 2n minus 1 all over n as our general term. And there's the first three terms and the general term of the series for h prime of x. All right, that's where we're going to call it quits for this video. Looks like we're going to come back for one more video in the course, the final video, section 10.15, video number 2. Feel free to join us for that one. And have a great rest of your day here, folks, and we'll see you next time for the final video. All right, bye-bye now.